Hello everyone, welcome to chapter 8.4 Chemical Properties of Aliphatic Alcohols. So in this video, we are going to look through substitutions reactions, include the reactions with sodium, esterifications, dehydrations, and nucleophilic substitutions using the following reactants. And then we are going to look through the oxidations, which will have the strong oxidations, using the strong oxidizing reagents and mild oxidations using mild oxidizing agent. And then here is your chemical test. So reactions with Lucas reagents, and this is called as Lucas test to differentiate the class of alcohols. And then last, iodoform test, which is to identify the presence of methyl carbonyl group. Alright, so first of all, let's look at these substitutions reactions, which first we include the breaking of OH bond and then substitute the hydrogens. Okay, so breaking between the O and the H and then substitute these hydrogens. And then secondly, break the COH bond over here and then substitute the OH group. So general formula, RH will represent your aliphatic alcohol. So when you react with sodium, okay, so for this case, we are breaking the OH bond. So hydrogen is substituted with the sodium cation. So you are forming a sodium alkoxide and ionic salt, and then it will release hydrogen gas. Okay, reactions between alcohol and the metal release hydrogen gas. And then second is the esterifications. Okay, so this process is the reactions between alcohol and carboxylic acid under the presence of an acid and then hot condition. So this esterification is a reversible process. So for this alcohol, we are going to break the OH bond, and then the hydrogens is going to combine with the OH from this carboxylic acid. So we are going to expect an ester. Okay, so the side product, hydrogens from alcohol, OH group from the carboxylic acid to produce H2O. So remember that where you break the bond is where you create the bond. So from this C double bond O, it would connect with the O from the alcohol. So for your next reactions is alcohol react with concentrated sulfuric acid under hot condition. This is an elimination process. Okay, a dehydrations. We remove one molecule of H2O from this alcohol to generate an alkene. And then there is a side product H2O. So for this dehydrations process, we're going to apply Say's rule. So this one you can revise back in chapter 5.2. Next, we have another type of substitutions in which the alcohol react with HX. So this halogen X is going to substitute OH group. So for these reactions, we are breaking the COH bond and then replace or substitute the OH group. So we are going to form haloalkene. So X replace OH, and then there is a side product of H2O. And the next one, we have reactions with the PX3. So either is PBr3 or PCl3. Okay, we only use chlorine or bromine. So the bromine or the chlorine will replace the positions for this OH group to get a haloalkene as well. So the differences here will be your side product. So reactions with the PX3 will produce H3PO3, the phosphoric acid. And then the next reactions with PCl5, only PCl5. Okay, and then you're going to produce chloroalkene, side product POCl3, and HCl as the side product. And then lastly, reactions with the SOCl2 in pyridine solvent. You're going to expect chloroalkene with the side product SO2 and HCl. For this SOCl2, it has a name, thionite chloride. So please jot down the name as well. And then pyridine is the solvent. So still we're using Cl only to replace the OH with chlorine. Next, let's try for this example as we can practice the naming of these structures as well. Okay, positions OH at carbon number 2. This is our 2-butanol. Okay, 2-butanol. So when this 2-butanol react with sodium metal, it's going to replace the hydrogens to create this salt. Okay, so the OH become O negative and A plus. and you have a side product, which is the hydrogen gas. The second reaction here is esterification. You have a carboxylic acid here. Again, you are going to observe hydrogens from alcohol will combine with the OH from carboxylic acid. Okay, so what we are going to expect is an ester. Okay, so if you pay attention to the structures here, you have 4 carbon in the alcohol and then positions number 2 with an OH group. So positions 1, 2, 3, 4. So second positions here attached to the oxygens. So this is actually your new bonding form. Okay, the one that highlighted in yellow is the bonding between an alcohol and the carboxylic acid. Okay, so the carboxylic acid here you have a CH3, C double bond O. And don't forget that here is a side product H2O. So the next one, we look at the reagents conditions. We have concentrated sulfuric acid. So this is a dehydration reactions in which we need to remove a molecule of water from this 2-butanol and generate the major product. Okay, you may want to write the minor product as well, but here are only written one. Okay, so according to Sayzev rules, the most highly substituted alkene will be the major product, and also your side product H2O. So the next reactions here, we have reactions with the HBr. So bromine will substitute the CO bond. So the one that in green color is the substitutions for the OH group, in which we break the COH bond. Okay, so bromine replace the positions for OH, and you're going to get this 2-bromobutane. Okay, and then you have a side product H2O, hydrogens from HBr, OH from the alcohol. For PBr3, also the same thing. We're going to expect the 2-bromobutane, and the side product is different. In this case, we produce phosphoric acid, using PBr3. And then if you are reacting the alcohol with PCl5, we are going to create 2-chlorobutane and the side product POCl3 and HCl. And finally, when this alcohol reacts with SOCl2 in pyridine solvent, you're going to observe the haloalkane as well, but the side product now change into SO2HCl. Alright, next, let's look at the oxidations of aliphatic alcohol. So for these oxidations reactions, the product depends on the class of alcohols and the strength of oxidizing agent used. So we have a strong oxidizing agents, which is a strong or harsh conditions, and you have hot acidified potassium permanganate, or you can also use sodium dichromate, potassium dichromate, or the chromic acid. And then we have the mild oxidizing agents, which is the mild conditions, PCC in CH2Cl2. So please take note on the full names of this PCC, which stand for pyridinium chlorochromate in dichloromethane. So depends on different class of alcohol. So if you have the oxidations of primary alcohol, and then you need to look at the strength of your oxidizing agents used. So let's say a primary alcohol react with a mild oxidizing agent, PCC in dichloromethane, you're going to produce aldehyde. If this primary alcohol react with a strong oxidizing agent, it's going to produce a carboxylic acid. So remember the process of oxidations, we either put in oxygens or we take out extra hydrogens, okay, on the carbon attached to the OH group. Alright, so next, if you have the oxidations of secondary alcohol, it will only producing ketone as the product, regardless of what type of oxidizing agents used. So secondary alcohol, either it react with the mild oxidizing agents or strong oxidizing agents, both will give you the ketone as the product. And for tertiary alcohol, it doesn't undergo oxidation reactions as there is no hydrogens attached to the carbon bearing the OH group. So it doesn't matter what oxidizing agents used, you're not going to observe anything. So we just write no reactions for the equations. So let's try the example questions number 1. So for this structures in part A, you have a OH group attached to a primary carbon. So this is your primary alcohol. And then using the PCC in dichloromethane, this is a mild conditions oxidations. And then for this KMnO4 in the presence of acid under hot conditions, this is a strong oxidations. Alright, so it will producing two different products. So primary alcohol under mild oxidations, you're going to generate an aldehyde. So from CH2OH into C double bond OH. And then under the strong conditions, you're going to produce a carboxylic acid. So for this strong condition, you need to make sure that there's no more hydrogen attached to this C double bond O, the carbon here. For the second structures given over here, you have your cyclopentanol, which is a secondary alcohol. So doesn't matter what type of oxidizing agents you're using, we're going to generate a ketone. Okay, so from a C single bond OH into C double bond O. The extra hydrogens is being removed. So oxidations, you insert oxygens or you take out extra hydrogens. Alright, next let's look at the identifications test for alcohol. The first test we have is Lucas test, and the function is to use to differentiate between primary, secondary, and tertiary alcohol, and to differentiate between alcohol from the other compounds. So the reagents and conditions for this Lucas test is we named this as the Lucas reagents, which is made up of concentrated hydrochloric acid and zinc chloride. And this is the general equations for these reactions. So an alcohol reacts with Lucas reagents to produce an haloalkane, and the side product is water. And then for different class of alcohol, they will have different observations. If primary alcohol react with these Lucas reagents, you are not going to get any product. So the observations will be no cloudy solutions form at room temperature, even after 15 minutes. For secondary alcohol, you're going to observe cloudy solutions form within 5 minutes, and tertiary alcohol, cloudy solutions form immediately. Alright, so next let's look at some of the example questions. And this example question is an extra one, and you may jot down somewhere in your notes under the topic Lucas test. Okay, so given the first structures over here, this is the structures from just now. This is a primary alcohol. So when you react with this Lucas reagents, there will be no reactions. Okay, and then the observations, no cloudy solutions form even after heating for 15 minutes. Okay, so doesn't matter is at room temperature or after heating, you will not get any products. So primary alcohol, a negative result. And then for this 2-butanol, this is a secondary alcohol. So under the Lucas test, you're going to get a product which is your chlorobutane, okay, a haloalkane and a side product H2O. So the observation for this secondary alcohol will be cloudy solutions form within 5 minutes. Be specific about the time. And then lastly, if you have a tertiary alcohol under the Lucas test, you're going to get these haloalkanes as well. So tertiary alcohol give you a tertiary haloalkane. And the observations, cloudy solutions form immediately. The next identification test is iodoform test. And this test is used to detect the presence of methyl carbonyl group. So methyl carbonyl groups, that means you can see this CH3 methyl group, and carbonyl means that this carbon's having an OH group, and then you will attach to the other alkyl group. So this is a methyl carbonyl group. And make sure that in this carbonyl group, you have at least one hydrogen present. So the reagents and conditions for this iodoform test, we need to have excess iodine in the presence of a base. So a base, you use NaOH, KOH, or simply OH minus. So in this iodoform test, there will be a cleavage between this methyl carbonyl group, and it will produce carboxylate ion and iodoform. Okay, so this will be the general equation. So in these structures, in this alcohol, you can see a methyl carbonyl. So this is a methyl carbonyl group. So when they react with this excess iodine in the presence of base, we're going to see a cleavage. So this cleavage is between the methyl and the carbonyl group. So from this CH3, you are going to form iodoform. Another name for this iodoform is called as triiodomethane, CHI3. It's a solid which will have a light yellow color. So we call this as a light yellow precipitate. And then the remaining structures over here, it will oxidize into a carboxylate ion. So this process, this iodoform, also considered as an oxidation reactions, in which if you observe at this C double bond O here, no more hydrogens is attached to this carbon. Okay, but overall the number of carbon will still be the same. If let's say, for example, I have 8 carbon in the starting alcohol. Okay, so over here iodoform itself carried 1 carbon. So for your carboxylate ion, you will have the remaining 7 carbon. So this is example. It depends on how many carbon you have for this alcohol. Okay, so iodoform observations will be light yellow precipitates form. So this is only if you have this methyl carbonyl group present. All right, so next let's look at the example questions. Again, this example you need to jot down somewhere in the notes. Okay, and some extra questions using the structures of 2-butanol. So in these structures, you can identify a methyl carbonyl group. So this is your methyl carbonyl. So under excess iodine and in the presence of base, we're going to break up this bond. This methyl group is going to form a iodo form. So CHI3, your triiodomethane. And then the remaining 3 carbon will be your carboxylate ion. 1 carbon, 2 carbon, and 3 carbon. And here is your carboxylate ion. And because you are using NaOH as the base, so the sodium ion will then combine with this carboxylate ion. Okay, so the total number of carbon in this initial alcohol, you have 4 carbon. So 3 carbons in your carboxylate ion, 1 carbon in your iodo form. Alright, so the next example here we have a 2-methyl 2-propanol. So this 2-methyl 2-propanol, even though you have a methyl group attached to the carbon with this OH group, but since the carbon attached with your OH, so we are referring at this carbon, it doesn't have any hydrogens, so it will not undergo the oxidation reactions. Therefore, for this iodoform test, it will have no reactions and no light yellow precipitates formed. Alright, please have a try at this example questions number 1, A and B, and questions number 2 to propose a chemical test. So I'll see you in the next video.